Okay, so question 7 here, maybe one of the trickiest questions, either this or question 6, probably one of the two toughest ones. But the key here, so they've got Sputnik 1 launched in orbit around the Earth in 1957. They give us the closest approach, and then they give us the furthest point away. And again, the key understanding is the closest approach is going to be, and obviously my ellipse is not very good here, but the closest approach is going to be kind of this peak of the ellipse over here, and then the furthest approach is going to be the exact opposite side of that. Right, so the reason that they gave me those two key figures is because together those two will help us make up the major axis. They'll give us the total major axis of this ellipse. Right, they'll give us the longest distance across the ellipse here. But anyway, they're asking me what is the speed when it's at its perigee, perigee. So when it's the closest here, what is its speed at that point? Now here's where you have to be very careful. We cannot just use the orbital velocity that we're used to. We cannot just do g equals m over r, right? Even though it does give us that altitude, it does give us that height, if you will, to that location, we cannot use this equation because it's not a uniform circle, and therefore it does not maintain that speed the whole time, so that is out the window there, right? But what we can do is we can take advantage of the ellipse and finding our semi-major axis. So again, the key for anytime we're dealing with ellipses, we want to try and find A. And because they give me both of these measurements, and I know that the total major axis would be 2A, it's easy enough to then find half of that, right? It'd be easy enough to find A. And so that's going to be the first thing that I do. I'm going to take my two measurements that they give me, so 6.81 times 10 to the third, or 10 to the 6, excuse me, and then plus 7.53 times 10 to the 6. So I've got both of those measurements. I'm going to find the sum of those two because, again, collectively those make up my major axis, right? So I'm going to add those two together and then obviously divide by 2, right? So I add those two up, divide by 2, and when I do that, I get that A equals 7.17 times 10 to the 6th meters. And obviously that measurement makes sense for me because it is bigger than this number, smaller than this number, and in fact, obviously somewhere in between, right? But in any case, so I've got my semi-major axis, which now would allow me to use any of the information that I can. So if I needed the period, I could try to use the period of the orbit. I could do the t squared equals, right, my 4 pi squared a cubed over gm. If that was helpful, I could do that. I could try and do some of my orbital velocities from that as well. However, the easiest thing, what I would recommend doing here is actually, again, thinking in terms of energy. Because if I can find the total energy at one point, I know the total energy everywhere. Right? So if I can find my total energy at this location of A, which I can do, right? This goes back to the how do I find the total mechanical energy for an elliptical path? Well, the total energy equation, the one that we derived by, again, using kinetic energy and potential energy, right? When we represented all of these in terms of G, M, M1, and M2, I should say, and then R, when we represented both of those in terms of that, we ended up getting negative G, M1, M2 all over R, or excuse me, over 2R when I actually solved the energy equation, right? The only difference for an ellipse is instead of R I use 2A. So my elliptical energy equation, if you will, is this whole expression right here. So then this would represent my total energy for the satellite as it's in orbit. Now if you start to look through the information, obviously we know the universal constant. They give us the mass of the Earth, right? We know the mass of the Earth. And then I just found my measurement for A. I found my semi-major axis. I don't know the mass of the satellite, and at first that looks like it might be a little bit concerning. But again, as soon as we realize that the total energy is conserved, so this expression which I just found, the negative G M1 M2 over 2A, would be equal to the energy at any particular location. And now I can take advantage of finding the kinetic energy and the potential energy at that shortest distance, at that nearest distance where I want to find the velocity, right? I know that the total energy would be equal to the kinetic energy and the potential energy at that location, at point P there is what I'll call it, right? But I can set that up. The reason I'm going to do that is when I start to break this up, well, this is 1/2 mv squared, where obviously the mass would be the mass of the satellite, and then this here we know would be negative G M1 M2 over R. Again, M1 I'm using as the mass of the satellite. So at this point, since each term has the mass of the satellite, I can obviously cancel that out. I can get rid of that. So looking through this expression, as soon as you get this set up, and as soon as you've found for A, you actually have all the other variables except your velocity, which is what you're looking for. You know G, you know the mass of the Earth. We found A. You're looking for the velocity. Again, you know G, you know the mass of the Earth, and you know the distance, the radius at that nearest position, right? You know the height at that nearest position. So it really is just a numbers game now, right? I just need to plug in all of my measurements and be very careful about my calculations. So 6.67 times 10 to the negative 11th, representing my G. Plugging in the mass of the Earth, which they gave me, 5.98 times 10 to the 24th. And then again over my 2A. So I guess I actually didn't define A. I could have just left it as 2A, but that's okay. 2 times 7.17 times 10 to the 6th. So that would be the left-hand side. Once again, notice it is very important that I make sure this is a negative quantity. Otherwise, it does throw my answer off. It makes it work out to be a negative kinetic energy, which obviously is not good. But solving this the rest way, and I know you guys, if you take your time, can calculate this without too much trouble. I certainly hope we can without too much trouble. So I'll just write this out, and then I will write down the final answer that I got from doing this. And then we're using the nearest point, so 6.81 times 10 to the 6th. Okay, so again, setting it up, plugging it in, and then just calculating, being careful that you calculate this as you go through. The final velocity should end up being somewhere around 7,840. I think 7,842, depending on where you rounded. But we'll go ahead and use some sig figs here and say it's 7,840 meters per second. Right. So again, the trick to this question, I cannot just use the orbital velocity. Right. I cannot just do this if it's an elliptical path. That's out the window. But what I can do is I can find the total energy by finding the energy at that A, at that semi-major axis location. Right? I can find the total energy there, and then because I know energy is conserved, I can relate that to the energy wherever I want. So whether it was the closest location or the furthest location doesn't make any difference. I just set it up, I plug in the location that I'm looking for, and I can find my velocity at that location as long as I can calculate this expression. But anyway, hopefully this question makes sense. Like I said, this is probably one of the toughest two questions on this homework assignment. So if this is something that gives you trouble, just make sure you let me know so I can help you get more practice with this. But hopefully it wasn't too Alright, so question 8, the final question of this homework, and I couldn't resist throwing in part B here. As I typed up this question, I constantly saw visions of Armageddon in my head, and so of course the correct answer for part B is the incredible music of Aerosmith, right? And so just enjoy for a moment. I will turn this off momentarily. Alright, that's probably about enough of that. Alright, well, back to physics. But anyway, okay, so part A here is what is the meteor speed as it hits the Earth? Hopefully this question actually isn't too bad. So they tell us the meteor is heading straight for the Earth. It has a speed at that location when it's at the moon's location. So we've got our Earth, here's the moon, here's the meteor heading towards us, traveling with that speed, and again at that distance away. The reason I say that hopefully this isn't too bad is if you boil it down to an energy equation, it really isn't a terribly difficult problem. We know that at this location, at the moon's location, it would have both kinetic energy and potential energy, right, based on the altitude between the Earth. By the time that it hits the Earth's surface, it would still have some potential energy based on the radius of the Earth, but then obviously it would have much more kinetic energy because it's losing some potential energy from this location and converting to kinetic energy. Really, so as soon as we set that up, as soon as we make that that realization there, hopefully this question isn't too bad. So again, I've got the kinetic energy at the moon and then the potential energy at the moon. And so I'm going to use M to represent at the location of the moon, not the kinetic energy of the moon, but at that location. And then the final kinetic energy, right, which is what I'm looking for to help me find the speed, and then the final potential energy, which I do have to be careful not to say that this is 0, because I am still the radius of the Earth away, right? So the potential energy is not something I can just neglect here. It is something I have to consider, and so that's where on this question I should have thrown the radius of the Earth back in. I didn't do it because you've seen it several times already in the homework, but the radius that I'll work with for the Earth is 6.37 times 10 to the 6th. So I'll just go ahead and use that value for the Earth's radius. But anyway, let's go ahead and look at the actual calculations then, just to make sure we're all okay with this. But my hope is it's not too bad from here. Right, as soon as I set this up, it's just a matter of plugging things in. So the kinetic energy at the moon's location will be 1/2 the mass of the meteor, which I don't know, but I do know the velocity is 14.8 kilometers per second, so 14,800 meters per second, which obviously I would square because it's kinetic energy. And then plus the potential energy. And keep in mind, as always, when we're dealing with the gravitational potential energy, we do need to be defining this as a negative value. So again, it'd be negative g, so it'd be negative 6.67 times 10 to the 11th, the mass of the meteor, which I don't know, and then the mass of the Earth, which I do know, 5.98 times 10 to the 24th. So again, taking that from one of the questions before, I do need that information. And then the distance to the moon's location, which they do give me here, right? 3.84 times 10 to the 8th. So this would represent the total energy that it begins with, and then obviously I'm running out of room, so I'll just set this equal and then throw it down here beneath it. But 1/2 mass times the final velocity squared, which is what I'm looking for, and then plus, or I should say maybe even just minus, but plus a negative, once again 6.67 times 10 to the 11th, the mass of the meteor, the mass of the Earth, which I know, and then the radius of the Earth, which again you need from a previous question, but I'm going to use 6.37 times 10 to the 6th, and then that's going to be what I set this top expression equal to. So if you look through here, at first, yeah, it is a little bit concerning. We don't know the mass of the meteor, but ultimately, since it's in every term, I don't need it. So then when you look through here, we have all of the variables except the final velocity, which is what we're looking for, right? We're looking for what is its speed as it hits the surface of the Earth. So the final velocity ends up being about 18,498, so about 18,498 meters per second, or if you want to convert that back to kilometers per second, about 18.5, if we round it off a little bit there, kilometers per second. So maybe answering that way to keep it consistent with the original answer, but it obviously does pick up about 4,000 meters per second worth of velocity as it's then traveling.